Okay, before the break we were talking about various esterifications. We looked at the Fischer Esterification, and in my Fisher Price guy, very interested in Fischer Esterification. And you recall that had a carboxylic acid and an alcohol forming an ester with the help of sulfuric acid as the catalyst. After that we went to hydrolysis of esters. Let me turn the page. And with ester hydrolysis, recall this is the opposite, the reverse mechanism of Fischer esterification. You start with the ester and add H2SO4 as our normal acid of choice, and we come up with the alcohol and the carboxylic acid. The mechanism is the reverse of the Fischer esterification. We also noted that you don't have to have it in acid. You can do hydrolysis of an ester with base. And when you do hydrolysis of ester with the base, it is saponification. Note also that you end up with the carboxylate and the alcohol because we are under basic conditions. All right, that catches us up to about where we were towards the end or beginning of the break. So let's move on now and let's look at amides. Recall, compared to our other RCOZ compounds, amides are really not wanting to do any nucleophilic substitution. The NH2 minus leaving group is a horrible, horrible leaving group. You're just not going to be able to substitute that off doing acyl substitution. So what reactions can amides do? Well, they will also do hydrolysis. If you start with an amide and add some aqueous acid, you will end up with the carboxylic acid and a protonated amine. We're going to break this carbon-nitrogen bond here, make the carboxylic acid and the protonated amine. An example right here, if we have this amide, you can see that we've just broken this carbonyl carbon-nitrogen bond. This side becomes the carboxylic acid. We just add an OH there, and we add a proton to this nitrogen here to make this amine. We're under basic conditions here. So we end up with the carboxylate and the regular amine. Under acidic conditions, you end up with the carboxylic acid and the protonated amine. Note, this is very important because of the protein you ate for breakfast this morning. This is what your body does. Recall, with proteins, you have amino acids strung together and they are connected through this amide bond. The peptide bond is an amide. The carbonyl carbon of one amino acid bonded to the nitrogen of the amine of the other amino acid. And in your stomach, we've got HCl, hydrochloric acid, and that will hydrolyze this amide bond, break the protein up into its component amino acids. Something to note, in your cells you don't have excess base or excess protons. pH is about 7, so reactions need enzymes, the body's catalysts, to run in pH 7. Okay, the last section of this chapter, right before the exam, we're now going to look at nitriles. And here I'm not too concerned about the mechanisms. They are in your book. Feel free to look through all those mechanisms. They are amazing and wonderful, as all mechanisms are. But right now we're just interested in, okay, if you have the nitrile, what's the product? And the first reactions we can look at are hydrolysis. If you have a nitrile, add aqueous acid, you will get the carboxylic acid and the protonated amine. Now, where have we seen this before? Ah, that's right. We saw it up above with the amides. So this kind of gives us clues that the mechanism for hydrolysis of a nitrile probably goes through the amide at some point. Note also, if we hydrolyze the nitrile with aqueous base, we get the carboxylate and the amine. So yeah, they go through the amide. The mechanism goes through the amide. At this point, I'm just worried about you knowing the products of the hydrolysis of the nitrile. Let's turn the page and look at some other nitrile reactions. Note, you can reduce nitriles with our good, nice, powerful reducing agent, lithium aluminum hydride. Followed by aqueous workup, you can convert the nitrile into the primary amine. Recall reduction, definition of reduction is addition of carbon-hydrogen bonds. This carbon gains 2 hydrogens to become CH2, and the nitrogen gains 2 hydrogens to become NH2. We add 2 equivalents of H2 across the triple bond to make the primary amine with lithium aluminum hydride. If instead of lithium aluminum hydride you went for dibalh H, recall that's a less powerful reducing agent, followed by aqueous workup, a nitrile becomes the aldehyde. So you can actually go straight from nitrile to aldehyde with this reaction, with dibalh H. So let's look at some reactions we can do. What would happen if we had ethyl bromide here and we reacted with NaCN? Well, let's think about this. Bromide, good leaving group. Cn minus, that's a good nucleophile. Cn minus will attack this carbon and we'll put a cyanide on here. But when you have CH3, CH2, C triple bond N, we're going to now call that a nitrile. And so that puts this C triple bond N in place of the bromine here. Dibalh H, well, what does dibalh H do with nitriles? Makes the aldehyde. So the second step here, combined with aqueous workup, will give us our aldehyde. All right, let's do another reaction. Start with our ethyl bromide again and react NaCN. The cyanide replaces the bromine in an SN2 fashion. Lithium aluminum hydride reduces it to the amine. So note, we went from CH3CH2Br to now CH3CH2CH2NH2. It has the effect of adding another carbon into our chain. And our last part of this chapter, organometallics and nitriles, they form ketones. If you have a Grignard or an alkyl lithium, that will attack the carbon of the nitrile, but it turns out the nitrogen is going to leave. We will not worry about the mechanism. You will get R prime attached to that carbon, and that carbon, instead of being triple bonded to the nitrogen, will now be double bonded to an oxygen. So that's the basics of the nitrile reactions. The exam is coming up, so learn all this stuff.